Guys, this is Ashita from Fourth Degree section. Now, I am here to present about simulation and coordinated control of hybrid microgrid under the guidance of Hemankesh Volu sir. Coming to the outline of our presentation, objectives, introduction, existing model and its block diagram, and its simulation circuit, and its limitations, proposed model and its simulation circuit, and output waveform results, advantages, conclusion, futures. Coming to the objectives, a hybrid microgrid considering both AC and DC sources, energy storage components, loads, and renewable energy sources. The main outline control objective related to this project is about voltage and frequency stabilization within the hybrid microgrid to establish acceptable ranges and operating limits for voltage and frequency. Here we use advanced control techniques that are MPPT control technique and PID control technique. Like MPPT control techniques such as perturb and observe technique. Like the MPPT technique we use in the solar because the tracking of a sunlight, like maximum power point tracking. PID control technique. It is an instrument used in industrial control applications to regulate temperature, flow, pressure, speed, and other process variables. Like to stabilize or to get a continuous output, we use a PID control technique. Coming to the introduction, this project aimed on the design and implementation of hybrid microgrid at addressing the dual challenges of voltage and frequency stabilization through the applications of advanced control techniques. Implementing a hybrid AC DC microgrid with advanced control strategies to stabilize voltage and frequency, thus addressing the challenges inherent in integrating diverse energy resources. Microgrids are crucial for enhancing energy resilience and sustainability in the face of increasing demand for decentralized energy generation and the integration of renewable energy resources. To stabilize the voltage and frequency, this is the main critical challenges in microgrids. Coming to the block diagram of existing model. Existing model is a DC microgrid. Here we use a solar and battery. And this solar PV cell is connected to the DC-DC converter and battery is connected to the bidirectional DC-DC converter, and these are connected to the DC bus via loops. And when solar energy is available, then PV cell will convert the energy, that light energy, into the electrical energy, and DC-DC converter will increases the level of the voltage. The increased level of voltage will be given to the DC bus and it is supplied to the DC loads. And if the level of voltage level is more than the DC loads, then the remaining energy will be given to the battery to store in it. If when the solar energy is not available, then battery supplies the energy to the DC loads. This is the main aim of the DC microgrid. This is the circuit diagram of a PV model. This is the equivalent circuit of a PV cell. And this is a boost converter with MPPT control technique with a PV array. This is connected to the PV array via MPPT PIR control technique. And it will increase the level of voltage and it will supply to the loads. This is the circuit diagram of a battery bank. Battery connected to the DC-DC buck boost converter, which increases the level of the voltage and it will give to the loads. This is a simulation circuit of a existing model. This is solar, PV array, battery, and radiation. Here we measure the radiance. The light energy will fall on this and it will convert the energy and it will supply the loads. And this energy supplied to the loads, if remaining energy will supply to the battery by using a connection of these switches. During charging, this switch will be closed. During discharging, during charging, the switch will be closed. Coming to the working of the DC microgrid without controller. Without controller, a DC microgrid without control techniques operates in a more basic and manual fashion. It lacks the advanced features such as dynamic optimization, fault detection, and automated load management that control techniques provide. While such a system may still function, it may not be efficient, resilient, or adaptable as a microgrid with advanced control strategies. Coming to the working of a DC microgrid with control techniques. By using the control techniques, A DC microgrid can dynamically adapt to changing conditions, optimize energy usage, and ensures the stability, making it a resilient and efficient solution for decentralized power generation and distribution. Coming to the drawbacks of a DC microgrid, it is only available for limited equipment availability. Like the using of DC loads is very less compared to the AC components. Coming to the voltage drop issues, there will be DC transferring of a DC voltages to the longer distances. There will be a reduction in the voltage. Limited standardization. There is a less standardization in terms of components and system architectures for DC microgrids. Challenges in islanding situations. In islanding situations, maintaining stable voltage and frequency is a challenging in DC microgrids or DC systems, and there will be complex control strategies for DC microgrids, especially in multi-source scenarios. It will be more complex in DC microgrid than compared to the AC microgrids, and we have to take safety concern on with high voltage DC. Coming to the harmonic issues, DC when power electronic devices are used in the DC systems, then harmonic will be produced in the DC microgrid, and there will be limited experience and expertise. And using of rapid switching of power electronic devices causes switching transitions in the DC microgrid, and will be considered on cost considerations. Using of power electronic devices, the initial cost of power electronic components is high compared to the AC counterparts. Coming to the proposed model is the combination of both AC and DC microgrid, so that it is called as hybrid microgrid. Here we use a PV, wind turbine, and a battery. These are connected to the DC bus, and this wind turbine is connected to the AC bus. This is a bidirectional DC AC converter, which converts DC voltage to the AC voltage and the AC voltage to the DC voltage, so that it is called as bidirectional DC AC converter. This is the block diagram of proposed model. DC microgrid. This is totally a DC microgrid, and this is totally about a AC microgrid. There will be a connection between the AC and DC microgrid by using a bidirectional DC AC or AC DC converter. Coming to the working of a DC microgrid without AC DC microgrid without controller. Without control technique using AC DC microgrid, without specific control techniques cannot be functioning effectively to a certain degree, and the advanced control methods are crucial for optimizing the microgrid's performance and enhancing stability and enabling efficient energy management. Because the control techniques provide dynamic adjustment and coordination of power sources, storage, and loads to respond variations in demand and supply, ensuring reliable and stable operations. This is the working of AC-DC microgrid with control. By using the control technique, by combining AC and DC elements and employing advanced control techniques, this microgrid configuration aims to maximize the efficiency, reliability, and sustainability in energy generation and distribution. It offers a versatile solution that can adapt to varying renewable energy inputs, storing conditions, and load demands. This is the simulation circuit of a proposed system. This is the DFIG wind turbine. This is solar. These two are the AC loads. This is the DC load. This is the grid connected via the step-down transformer. This is the battery. And this is the solar. And this is for battery measuring. And these two are for measuring the AC load. And this is for measuring the battery. And here we can measure the DC load output waveforms. Here we can measure the value of a battery. Here we measure the irradiance. It will convert the falling on sunlight. It will supply energy either AC loads or DC loads, and it will from here it will take energy to the loads. And if energy is more, then it will supply to the battery. It stores the energy. And then when solar is not available, then battery will supply the energy to the DC loads. This is a simulation model of PV panel. Inside the PV panel, how they connected. This is the solar and connected to the DC link and a grid inverter and inverter control technique, MPPT control technique. These are connected inside the solar. This is the wind turbine, how interconnected. This is the induction generator and a transformer is connected to the AC-DC AC converter, which converts AC voltage to DC voltage and DC voltage to AC voltage to supply to the AC loops. The existing model waveforms using a DC microgrid, when without using a control technique, the output voltage is nearer to 49. When using a control technique, the voltage is up to around 150. The battery waveforms are without control technique and with PID controller technique. We can observe. Coming to the proposed model waveforms, we can see voltage and frequency waveforms. There is a major change in the frequency waveforms, stable and voltage frequency. These are the output waveforms for a grid, PV panel, battery, and DC loads. There will be a continuous supply to the DC loads, and the grid power is also continuous. PV and battery power will changes according to the solar radiation. This is the grid power. These are the output waveforms of PV panel at different irradiation, and these are the DC load waveforms. This is the PV power and irradiance waveforms of supply to the PV. And coming to the comparison between the existing and proposed model values are existing model 186 watts and proposed model value is up to 228.735. And voltage, open circuit voltage and short circuit current, open circuit voltage and short circuit current. Comparing to the existing and proposed model, there will be a large variation. And the battery also there is a variation. And we will not use a wind turbine in the existing model, so that are not indicated. And we can observe in the proposed model. Comparing both the DC microgrid and the hybrid microgrid, there is a voltage level is large variation. Comparing of both voltage DC microgrid, the supply from only battery and PV. Here supply from the AC and DC components like solar and wind power distribution. Here in DC microgrids, the distribution of power for smaller distances. Here we can distribute for longer levels, because there will be no variation in AC voltages. Energy storage integration. Here we will use battery energy storage systems, avoiding the need for additional conventional systems. Here requires converters for integrating energy storage due to presence of both AC and DC components. And renewable energy integration, well suited for integrating DC-based renewable energy sources like solar panels, offers flexibility for integrating both AC and DC renewable energies. Conversion losses. Generally experience low conversion losses since there is no need for frequent AC DC or DC AC conversion. Here involves additional conversion stages leading to high losses compared to a purely DC system. Coming to the advantages, reduces multiple power conversions in individual AC or DC microgrid and allows connection of variable AC and DC sensors and their respective loads simultaneously. Microgrids will offer economic value to society by averting the loss of inventory and productivity during a power outage. This will attract high quality employers to a region, and as local energy plants, they create and keep jobs within the community. Coming to the conclusion, the utilization of advanced control algorithms, including model predictive control and PID control technique and adaptive control techniques, played a pivotal role in optimizing the operation of hybrid microgrid. In real-time monitoring and sensing systems, coupled with fault detection and resilience mechanisms, enhanced the microgrid's reliability, enabling it to respond dynamically to changing conditions. Coming to the future scope, the next step is to consider the microgrid as a system, understanding how its power sources interact. The control of power system may be embedded in power electronics, using specialized controllers for stability and efficiency. Once the interaction and relationship of power sources are defined, further development can focus on individual sources, considering additional variables. Thank you.